Acid-base equilibria, salts, and hydrolysis is the topic for today. Most of us recognize that an acid and a base go through a neutralization reaction to produce a salt and water, which is the case. However, this salt, depending on the acid and the base that it's made from, can actually interact with water itself and create a slightly acidic or slightly basic solution. So salts are not always neutral. If you have a salt that is formed from a strong acid and a strong base, then you'll actually get a neutral salt. So NaNO3 is coming from sodium hydroxide and nitric acid. So that's a strong base, that's a strong acid. It's going to give us a neutral salt because neither of the ions, sodium or nitrate, wants to gather the hydrogen or the hydroxide back up. It's going to be completely the other direction. For something that forms a basic salt, you're going to have a strong base and a weak acid. This new term right here, hydrolysis, basically means that it reacts with water and will actually split, like lysis, water. So the formation and hydrolysis of K2S, first of all, the K is coming from potassium hydroxide, and the sulfide ion, if we went to the acid, would be coming from H2S. This guy is a strong base. This guy is a weak acid. So when we do these hydrolysis problems, we're always going to be looking at whichever one is the weaker of the combination. So then we take the sulfide ion, and it interacts with water. Right here it has a -2 charge. It does not have any hydrogen, so the only thing this can do is act as a base. It can take a hydrogen from the water, so we get the HS- ion, and then we're left with OH-. So that's how we end up with the idea of the basic salt. Is this thing, the sulfide ion creates some hydroxide. All right, if we have an acidic salt, we have a very similar situation, only now we're going the sort of the opposite direction in terms of strong and weak. A weak base and a strong acid. This time we're looking at the cation, which is still going to be the weaker one, hydrolyzing the water. So if we look specifically at NH4Cl, NH4 is coming from NH3, which is a weak base. The chloride ion is coming from HCl, which is a strong acid. And so we have to sort of pick, again, the weaker one. This is what we actually have in solution, so we have to use that ion, NH4+. We're using the weaker of the two ions, plus H2O. Here we have ammonium ion. Gain or lose hydrogen is the question. This is as much hydrogen as nitrogen can hold, so it's going to act as an acid and give one of its hydrogens over to water to turn into NH3 and H3O+. So essentially what's happening in both of these scenarios is you're going from something that is charged, an ion of some form, reacting it with water to produce something that is neutral, and then either hydronium hydroxide depending. When you have a scenario where both components are weak, you actually have to compare the Ka and the Kb value to figure out which is going to be which. Whichever has the larger value Larger K will be the type of salt it's going to be. So acidic salt or basic salt will be determined. All right, so let's take a look at the first set of exercises here, exercise 3. We need to predict whether an aqueous solution of each of the following salts will be acidic, basic, or neutral, and prove it with appropriate equations. The first one that we're looking at is we have ammonium acetate. So this comes from NH3, and this comes from acetic acid. That's a weak base. That's a weak acid. Every time you do one of these problems, you should think through it just like this. Because they're both weak, we need to know the K values. You can get those K values out of earlier pages in your notes or from the back of the textbook in one of the appendices. The Kb for the ammonia is 1 times 10 to the negative fifth, or 1.8 times 10 to the negative fifth. And the Ka for the acetic acid is also 1.8 times 10 to the negative fifth. They just so happen to be equal. So what we have going on here is, based on the Ka and the Kb, I can tell you that this is going to be a neutral salt. However, because they're both weak, they are both going to hydrolyze. So if I truly want to prove it, I need to show both reactions. The ammonium ion reacts with water. It's acting as an acid here, so gives up hydrogen to make ammonia and hydronium. And then the acetate ion is acting as a base. Acting as a base, wants the hydrogen to make acetic acid and the hydroxide ion. Both of these things are happening, but since the Ka and the Kb are exactly the same, they're making equal amounts of hydronium and hydroxide, which will then form water. So then you get a neutral salt. NH4CN is a little bit trickier. This is coming from NH3. This is coming from HCN. We just use the Kb for this one. And the Ka for HCN is 4.9 times 10 to the negative 10. In this case, the Kb is greater than the Ka. So if I just want to know what kind of salt it is, it's a basic salt. I'm done. But I want to actually be able to prove it using some of the equations. So here we go again. The first one is just like we had. We had ammonium plus water makes NH3 and, H3O plus. We also have cyanide ion, because again we're using the salt. Want to neutralize that charge, so we get HCN and OH minus. Alrighty, so now if we look at these values, here's where you have to really think hard. Okay, if we look at the K, if we look at the ammonium, because we're doing that one first, Kb for ammonia is relatively large, but that's going the opposite direction that our equation is currently written. So if the Kb is fairly large, then the Ka, which is the way it's behaving here, is fairly small. Since the Ka is pretty small, that means we're not going to make very much product. For part C, it's actually a little even more tricky. You have aluminum sulfate, so again we have a salt. This comes from aluminum hydroxide. Sulfate's coming from sulfuric acid. So we have a strong acid and a weak base, because it's not one of our strong bases. So we have, since this is a strong acid, weak base, we're going to have an acidic salt. We're not going to use this one at all because it's a strong. It's never going to reconnect, I guess you could say. The hydrogen and the sulfate won't reconnect. So that leaves us with aluminum, which the aluminum is a little different in the way that it needs to be considered. Since we have hydroxide here, we don't really have hydroxide in this situation, but the aluminum ion itself doesn't really have a way to, kind of gain or lose hydrogen. So what we have to do is we have to consider it the way it actually exists in solution, which is as a complex ion. So we have hexaquo aluminum 3 plus water, and then we need to figure out what's happening here. We know that this is going to be an acidic salt, so that tells me that whatever happens, I need to get a hydrogen off of this aluminum and put it onto water. So let's kind of take a peek at what that might look like. So if I have aluminum in the center, and then I have 6 waters surrounding it. Okay, these are my little water molecules. All right. Because the aluminum is positively charged, it's very attracted to the negative or partial negative sides of all the oxygens. Means it's pretty easy for one of these little hydrogens to get yanked off. So this hexaquo aluminum ion loses one of its hydrogens to water, which leaves us then with aluminum. Now 1, 2, 3, 4, 5 waters. And then this is now lacking in a hydrogen, so this is just an OH. So if we look at the ion, it's a +3 charge. 5 water molecules are neutral ligands. This hydroxide is a -1 charge ligand, so that leaves me with a +2 charge right here. This is probably the most common one of these that you'll see, so it's probably worth keeping a decent eye on how to do this one. All right, for exercise number 4, I'm going to do 4 with you, and then I'm just going to give you the answers for 5 and 6 because they are very similar types of problems. I'll give you some hints though. All right, so we want to calculate the pH of a 0.3 molar NaF solution. We're given the Ka value for HF. We have a salt. It's formed from sodium hydroxide and HF. So we have a strong base and a weak acid. Therefore, we should have a basic salt in the end. That's kind of our goal. We want to know just how basic it's supposed to be. So we want to start off with taking, again, the weaker of the 2 ions. So we have F- plus H2O. The whole point of these salt ones, the hydrolysis, is essentially to try to neutralize whatever ion we started with. So since this is a negative ion, it wants to accept a proton to become the hydrofluoric acid, and then we'll be left with OH-. Okay, so since we're starting off with 0.30 molar, we don't care about water, 0 and 0. We are doing rice. If you're tired of rice and you know how to set the equation up, you do not necessarily need to set up this chart each time. But what we do have to be careful with is here for the next step. Here's where we plug our values in to Ka, or to K, excuse me. In this question, we are given the value for Ka, for an acid. Our reactant, what we actually have to begin with, is behaving as a base. So we can't use the Ka for this problem. What we have to look at next is we have to figure out what the Kb is first. We do that through Kw. Okay? We learned in the previous section that Kw was 1 times 10 to the negative 14th. So if I need Kb, then it's 1 times 10 to the negative 14 over 7.2 times 10 to the negative 4. And that gives me a Kb value of 1.4 times 10 to the negative 11. And then I can set up my sort of expression. X squared over 0.3 minus x. I'm going to assume that I can take that out for the time being. Multiply 0.3 times my Kb. Take the square root. And then I get that x is equal to 2.049 times 10 to the minus 6th. And that is equal to my hydroxide concentration. So from that, I can take the negative log and I can get the POH, which is 5.688. And from there, I can get the pH by doing 14 minus the POH. And I get 8.31. I'm going to go ahead and stop there with 2 significant figures because I had 2 significant figures in my concentration. Again, this first one and the pH is coming from the exponent, so these last 2 are my significant figures. So that becomes my answer. For exercise 5, the pH is going to be 5.12. Again, be careful about what the original ion is acting as. Is it acting as an acid or is it acting as a base? And then for number 6, the pH is 3.43. Again, we have the aluminum is the challenge there. And this is going to essentially be the same equation that we got in part C of exercise 3. So we're going to use that equation. This is your pH value. Again, be careful of how your original ion is behaving. Is it behaving as an acid or is it behaving as a base? Good luck.